Alrighty, so I double checked all of the base files for problem 3. Uh, this is just an instance of SolidWorks being weird because I followed all the same modeling techniques and it is exactly the same as far as the geometry goes. So this is probably just a slight difference in the way that it calculated the loft or maybe some slight difference in the way it did the dome. But in any case, the real lesson here should have been that I should have checked the model on different machines and just removed a sig fig from the end of the precision that we gave you. But yeah, as is the problem you can get with lofts and domes and sweeps, because they tend to be a lot more free form as far as geometry goes, and that can lead to some discretized methods of calculating volume, which can lead to a little bit of variation depending on exact specifics. But anyway, on to problem 4. So for this, we are going to be starting by downloading the Homer 4 problem 4 parts zip from Canvas. Then we want to go to our zip, go to 7-zip, extract 2. There might have been a different zip file or a zip thing that you may have used, but regardless, our first step is we want to extract all of the parts. Then this has some instructions. In general, it is a best practice to read all of the instructions first. So we're going to use standard mates to mate everything together to allow for the movement seen in the animations posted on the Canvas page. One component has multiple configurations. We want to make sure to import both. A subassembly of the button mechanism has been included with the spring set as a flexible component. I recommend using the subassembly. Remember that subassemblies must be made flexible to activate their mates. Then we're going to apply some colors as described on the next page, so we can see that we've got an item list with all of the different colors on it. They don't need to be exact, but they should be close. Fair enough. We're not going to be matching hex values and all that. Next up, apply our advanced and mechanical mates as described, and we will need some labeled dummy mates to pull this off. So you need a limit angle mate, a rack and pinion mate to connect the motion of the lid to the motion of the snake. We're going to need a screw mate so that the snake rotates as it goes up and down, and a linear coupler so that as the button moves in, the snake moves up. Next up, we're going to have a part that is too large for the subassembly, so we're going to have to edit that part file to have a snug fit. So we want the component to match in diameter to the thing that it fits within. Then we're going to use pack and go to compress our assembly and part files into a single zip and submit that file. And as a note, we are not going to be double counting mistakes. So that is pretty much just even if you aren't fully happy with problem 3, do problem 4. You won't get dinged. So, all right. The general motion that we're looking for before we do the advanced and mechanical mates is the lid needs to open, the button should be able to go in and out, the snake should be able to go up and down, and the snake should be able to rotate. Any motion beyond that would be considered leaving it not defined enough. All right, cool. So let's start by bringing in a initial component, and let's start by creating us an assembly file. So I'm going to open a new assembly, and generally you want to match your units to the units that are given for the model. So here we want to make sure we're in millimeters, but first it is asking us to import an initial component. Life gets a little easier if we set this to icons. There we go. Now we can see what we got. And we have a component labeled as the base. So that's probably a good one to start with. So we're going to open that. And then we want to place our initial component using the check mark, which is going to match the origin and the front, top, and right planes with the front, top, and right and origin of our assembly file. Cool. So there's that. We've got our initial component in place. We can go back up to insert components. And let's see, what else do we want? We want our button subassembly. I'm holding the control key so we can import multiple things at once. We want the hinge, we want the band, we want the shell, and I'll grab the actual part next. So the button gets placed there, hinge pin, put that there. For the band, we want one of them, and let's do the top one first, and the shell, we're going to need another copy. So I'm going to highlight it, select it, and Control C, Control V. So now we have a bottom shell as well. And for the band, we'll do the same thing. So Control C, Control V. But one of these bands I want to be the other version. So I'm going to right click on it in the design tree. We can go to configure component. We can change this to the bottom configuration. So I'm not actually going to be a stickler of which one of these is top or bottom. We just needed to label them, and that made sense. But for consistency, this one's going to be our bottom one, and this one's going to be the top one. So we'll sort of lay those out like that. And then the final component that we need to bring in is our result from problem 3. So we're going to just pop out, grab that, and place it around there. And to pretty things up, we're going to just hide that sketch. There we go. Cool. All right, now we have the long and arduous process of hitting the mate button a lot. So we're going to go up to our mates, and to make life a little less inconvenient, we're going to keep the keep visible pin pressed. And let's start with the bands, I guess. So we know that looks like that edge and that edge should be coincident. And then one trick with this is that the entire model is based off of cylinders, or based off of spheres, sorry. So if I just select the outer surface of that band and then the outer surface of the base at the bottom, those two will be concentric, and that should, yeah, that fully defines that component in place. And repeat a similar process. So bottom of, or inside of shell to outside of sphere, applies our concentric. Then I want another concentric going for those two. So that'll make it so the shell rotates but doesn't move. And then to finalize its position, we just grab one of these flat surfaces and the outside of our object there and set those to parallel. Cool. So there's that one. Now, let's get the other band set up. So I know that I want the cylinders to be concentric, but I want them flipped. So we're going to swap the mate alignment. Yeah, that looks about right. And then I want this surface on the inside of our object to match up with this surface there. Check mark. Now we can rotate that over. It looks like it should be in place. All right, next up, the other sphere. So I'm going to just do the cylinders first. So we got that one and that one. We're going to need to be concentric. Then we know that the spheres are going to be concentric. And then we know that the flat edges are going to need to be parallel. Cool. So testing it out, the hinge works. Still need to put the pin in it though. So we need the cylindrical surface on the outside of the pin and the cylindrical surface on the inside of the hole. Those are going to be concentric. And to mesh this in nice so that the flat, well, quote unquote flat, the pin stays completely within the hole, it's the same spherical trick. So that end surface is a section of a spherical surface. Oh, oops. That was one of the two other spherical surfaces that would not work the way that we want. So since the hinge pin is based off of this bit, we can pick, this one actually makes the most sense. So we'll select that surface there, and the concentrics will keep the pin snugly on the inside of the object. We can see a little bit of glitching here, where the two models are overlapping with each other. That may or may not be a problem that we're going to solve later on in the process. Let's do the button next. So this one's nice and easy. We've just got a rectangle, or like a rectangular bit there that connects into a rectangular bit there. I think the easiest way to do this is if we grab that corner and this corner and make them concentric or coincident. then we can grab that corner and that corner, make them coincident, and then bottom of the button, bottom of that cavity, make them coincident. Cool. Lastly, but not leastly, we have the actual snake itself. So we want the cylinder of that to match up with the cylinder of that. Keep those concentric, and that will behave the way we want. Awesome. Alrighty. Well, we are here. Let's create some dummy mates. So one dummy mate that's going to be handy is looking at our internal view. We can see that we want the snake to be able to be all the way at the bottom of that little cavity. So I'm going to move the snake out of the way. We're going to create a coincident to keep the snake down at the bottom. We are also going to want one to have the lid closed. So I'm just going to grab that flat surface there and this flat surface there. That'll be another coincident. And I just kind of put myself in a corner here because we also want to be able to change the orientation of the snake and the position of the button. So at this point, we'll X out of that. I need the button to be able to move, so we're going to right-click on our subassembly and set this to a flexible subassembly. So now I can push the button in and pull the button out. And we also want to be able to open the Pokeball again. So we're going to take, let's see, we did these two as dummy mates. So I'm going to hold down Shift to select both of them, right-click, add to folder, and we'll label this dummy. And we can suppress that. So now that'll let me open the ball back up. It's going to be useful to have a dummy mate that holds the button all the way out. So we get to use the same exact spherical trick. So that and that should be concentric. Check mark. And to orient the snake correctly, I'm going to actually use the primary planes. Since this isn't something where we actually specified anything in the problem statement, you don't necessarily need to have a dummy mate for the snake's orientation, but because I am the way that I am, we're going to add one anyway. And for the primary planes, if we take the front plane of our snake and the front plane of our assembly, those two will match it up so that, dang it, so that the snake is pointed the right way. Let's see if you ever get the funnel. I'm trying to remember. It's one of the function keys, gets rid of it. Yeah. Just not having much luck today. Oh, there we go. Yeah, it's F5. Or, yeah, F5. We can turn off the selection filter from there. There we go. Cool. Extra bonus lesson, I suppose. Alrighty, so got that. We'll move these two new mates into our dummy mate folder. And we'll suppress all of those. There we go. Now we can do some colors. So we're told that the upper one is red. Let's just bring up our colors menu. We can just kind of hide that. There we go. And pin this so we actually get to keep it. So we're going to apply these at the component level, so the changes will apply within the assembly, but they won't apply to the parts. And I want this top portion to be red. That looks about like red. We have parts 2 and 3 are black, so we'll set the black there. And 2 is the top bit of the band, and 3 is the bottom bit. Then we want 4 to be purple, so we'll select that, select our thing. That looks about purple. It's probably more of a magenta, but eh. We want 5, 6, and 7. So it's going to be 5 is the base, 6 is the pin, and 7 is the housing for the button. So all three of those are going to be gray. Set that to that. And then the bottom shell, the button, and the spring are all going to be white. So we'll pick our white, button, bottom shell, spring. Check mark. Cool. That gets all of our colors down. So got A, we got B. Next up is C. So for this, we want to apply our, let's do the limit angle first because it's the first one listed. Makes sense. Okay, go to that. The limit angle is an advanced mate, and it is the bottom one down here. And for an angle, it is easiest to measure an angle between two flat surfaces. So I'm going to select these flat faces here. We need the angle measured flipped from there, and there we go. I never actually know which ones are going to do which, but there's a total of 4 combinations between checked and unchecked and the mate alignment, so you can brute force your way through it and get the answer much faster than you could if you actually tried to think it out. So always remember, when there's a limited number of options, brute force is a perfectly valid method of going through it. So we want the minimum angle to be 0. We want our maximum angle to be 80. So we'll hit those two, check mark, and we test it. That looks like it is well within what we are going for. All right, next up, we want it so that we have a rack and pinion. So that's going to be on the mechanical. So we've got a rack and pinion. So that when the lid makes a full rotation, the purple piece moves up 16 or 67.5 millimeters. So the rotating part is going to be the pinion, and for us, the pinion is the middle sort of cylinder here, that face, because that's the part that is directly rotating about something. And the rack is the component that moves linearly. So we're going to select this bit there because that defines the component, and the linear direction is going to be the total distance it travels, or the linear direction is going to be the central axis of our rack. So for that, we want a rack travel per revolution of 67.5. So we'll hit our check mark, test it out. As the Pokeball closes, the snake goes down, and as it opens, the snake goes up. So we're good there. Next, we want a screw mate. So we'll select our screw while we're here. So the purple component makes a complete rotation or complete revolution relative to the base after 15 millimeters. So that would be a distance per revolution of 15. And we've got 2 things that we need to select. One of them is the component, and the other thing is the thing it is moving relative to. So on this one, we didn't have anything that specified the handedness of the rotation. So because of that, we can kind of just pick whichever. Well, but if we wanted to be consistent, I believe on the animation, we see that it is moving. So as it goes up, it moves counterclockwise. So we'll have to test that and see how it looks. So we've got that in place. Oh, oops. Did I screw up I screwed up something. That should not be spinning that much. Oh, yeah, distance per revolution, 15. There we go. So as it goes up, it goes counterclockwise, which does match what we see here. Cool. So we are being consistent with the GIF. All right, neat. So that's our limit angle, that's our rack and pinion, that's our screw mate. Now we have a linear coupler. So that is on the advanced mates since we don't have a nice and easy mechanical analog. And for this, we need to pick 2 things that specify linear direction of our components. So first, oftentimes the best thing for this is a flat surface that is moving perpendicular to its normal. So effectively, for the cylinder, since the cylinder is moving up and down, we want the top face because the normal vector of that face is vertical, and the face is going to be moving along that normal vector. So for that, we'll select that surface there. And we see it gives us a nice arrow to point out, oh, this face, you mean going that direction. So yeah. And we don't have a lot of flat surfaces on the button that we can see from the outside, but on the inside we can get to that flat surface there. And if we want to be real sticklers, we can then pick components that are going to define our relativity. So the snake moves relative to the base, and the button moves relative to the button housing. And we want a 1-to-1. I don't know which directionality it's going to be yet, so we'll just have to test it. Let's try reversing it. Whoops. There we go. Want that top surface there, and the base. Ah, okay. It was upset because the button was already at the furthest it goes. So, alrighty. At this point, we'll go back to our linear coupler, uncheck our reverse box, and now we need to go set up all of the advanced and mechanical fun stuff. So we've got our 4 advanced and mechanical mates. I'm going to hold down Shift, select the top one, select the bottom one, and then we're going to add them to a folder, add mech, and this is going to make the dummy mates dance much easier. So we're going to suppress the advanced mechanical, unsuppress our dummy mates, resuppress the dummy mates, and then unsuppress the advanced and mechanical. So that way we get through that with 4 clicks instead of the several dozen it would take if they were all separate. At this point, you can see that we can open the lid, close the lid. The button itself gets a little finicky, just because of the flexible component mostly, but I thought that it was cool enough for you guys to see what SolidWorks is capable of that it was worth the slight uh, iffiness of it. But another thing you might have noticed is when you are futzing with this, if you move quickly, and especially here, we can end up with a slight gap in it where it doesn't close fully. So that just comes down to the way that computers discretize moments in time. So if we move very slowly, we can get the gap to actually close. There we go. But that's not as important. We know it's set up correct now. Cool. So that is step C. Step D has us edit a component, and that is this one here. So first off, to show that there is a problem, we're just going to go over to Evaluate, Interference Detection, Calculate. Got that interference there. So we have one for the middle, one for the far end, one for the other far end. So this component is obviously too big for the hole that it fits in. So first thing that would be handy to know is how big is that hole? So you can find that if we go to the Pokeball band, and the hole is defined here via cut extrude 2. We've got a diameter of 3 from that sketch. So the pin, if we check our revolve, oh no, that's going to be in the cut extrude 1. That sketch, which is currently hiding the dimension, but anyway, if we go in and we edit that sketch, so we'll save our assembly first. So for part 4 demo, blah blah, everything gets saved. Oh, that's why that dimension isn't showing up. I defined this weird. Whoops. All right, there we go. So that is actually from Revolve 1, where we see that this is set to a height of 5 units. So if we bump this down to 3 to match with the size of the hole, hit our rebuild. There we go. That looks a lot better. And then we run another interference detection. We get no interferences. So that gets step D taken care of. Last up, we're going to use pack and go. So save our models. Then pack and go lives under files. Where is it? Pack and go. We want to save it to a zip folder. Browse to choose where we want to put it. So we're just going to call this for P4 demo and save. So now we can email that zip folder to someone and they would be able to extract the files from it and open the assembly and everything should work nice and easy. Cool. Well, with all of that, I believe we are finished up with the walkthrough for problem 4. There will not be a walkthrough for homework 5 because it is literally just following the tutorial. So hope you all had a good quarter. Hope that these videos have been handy, and yeah, best of luck out there.